Thank you, thank you everyone for coming. So in this lecture I will show you some of the fantastic results that we are obtaining with this fantastic telescope. And I understand this is quite a heterogeneous audience with people who are specialists in the field and other people who are from very different backgrounds. So I'll try to have the right balance in providing information that is, how to say, for everyone. Right, so the James Webb Space Telescope, what is it? Just, I'll start with providing some information about the telescope, and then I will start discussing a little bit more the result, focusing on the early universe. In one sentence, the James Webb Space Telescope is the largest telescope in space. And just for comparison, with its predecessor, the Hubble Space Telescope that was providing very nice images until a few years ago, the size of the primary mirror is nearly 3 times larger than the mirror of Hubble. And why does it matter? Why is it important to have a large mirror? Well, large mirror means you can collect much more light, and you can see farther away. And as we will see, so more distant galaxies, more distant stars, and as we will see, this implies seeing more into the remote past. Developing Webb has taken about 25 years. I myself have spent about 20 years of my career on this project, so quite a large, significant fraction of my academic career. And it's certainly the most expensive project ever developed for astronomy, $10 billion about. And just to give you a comparison, the most expensive telescope ever developed so far, or also planned for the near future, is about $1 billion. So we are talking about a big leap in terms of cost. So why so expensive, and why did it take so long to be developed? Well, it's big. It hosts a lot of totally new technologies which required a lot of testing. But the main thing is that it's very big, and to put this kind of enormous telescope in orbit has not been simple. To begin with, it wouldn't fit in any rocket if it was a monolithic mirror and a monolithic telescope. So we had to conceive it in a way that it could be folded and put in the head of a rocket, and then so deployed in space once launched. It was launched on Christmas Day of 2021 with the Ariane 5 rocket from the European Space Agency, and the launch was perfect, flawless. You may say, why is so how to say remarkable? Well. First, it's not so obvious that everything goes smoothly. You can, as you may know, some of the rockets can explode while being launched. So most of the astronomers didn't enjoy very much their Christmas launch, because we are all nail biting, hoping that everything was going smoothly. And then, once in orbit, it started the process of deployment. This is an animation which shows how the telescope deployed. Is very accelerated. The whole video takes probably about a few minutes, but in real time it took about 2 weeks. It was a very slow deployment. Now, keep in mind that the fundamental golden rule of all astronomical space missions is that you shouldn't have any moving parts, okay? So Webb had something like 200 deployment and release systems. So was quite a challenge to ensure that the telescope would deploy properly without any problem, because each of these movements would have been a single point of failure. And of course, why you don't want, in principle, moving parts, because if anything gets stuck, you don't have a way to go there and fix it. It's not like the Hubble Space Telescope. Indeed, you may see here that while the telescope was deployment, the video was showing the trajectory of the telescope, and you see that it didn't go orbiting around the Earth, not even around moons. It went far away, about 1.5 million kilometers away, which is where the so-called second Lagrangian point is located. It's a resonance point between the Earth and Sun. And why did we send the telescope orbiting there? It's because essentially Webb is a telescope that observes primarily in the infrared, and the infrared you don't want to have any body that radiates infrared light. So not only the Sun, but also the Earth and the moons, because also the Earth and the moons, which are relatively warm, emit a lot of infrared radiation. And that radiation would blaze the telescope, and also would warm it up, and if the telescope becomes warm, it would start radiating in the infrared and would essentially prevent to see the faint light of the galaxies in the distant universe. And the only way to have, so if it was orbiting around the Earth or the moon, essentially you would always have either the Sun, the Earth, or the moons on the way, and instead of staying in on the opposite side of the Sun in this orbit, it's possible to have these sun shields in such a way that the telescope is always in the shade of simultaneously the Sun, the Earth, and the Moon. Okay? The improvement in terms of performance with respect to its predecessors is fantastic. You can see here the improvement in terms of sharpness of the images with respect to some of the previous space missions in the infrared, and you can see how dramatic is the sharpness of the images with respect to what was obtained by the past telescopes. But is not this really the most important improvement of Webb? Is its huge leap in sensitivity. In these graph shows in the infrared the capability of the instrument on board of James Webb and previous facilities from ground and from space in detecting the light from the galactic objects and extragalactic and from the far universe. And in some spectral bands, at some wavelengths, the improvement in sensitivity is more than a factor of 1,000. Now, a factor of 1,000 is a lot. It's really huge. It rarely happened in the history of astronomy and more broadly in the history of science. Just to give you a magnitude of the improvement, it's essentially equivalent in the visible to suddenly upgrading Galileo's telescope to the modern large telescopes that we have today. So you can think sort of 400 years of discoveries compressed in 10 or 20 years of operations of Webb. So there's been a lot of expectations for what the Webb can discover, and that's the reason why the astronomical community and the scientific community has invested so many resources to develop this telescope. As I mentioned, the Webb is optimized to observe the light in the infrared, and that's why the mirror is actually coated with gold, because gold reflects much better in the infrared. And also is the reason, as I mentioned, for having these sun shields, which keep the telescope in the shade of the sun and Earth, and therefore allows it to cool to very low temperatures. Now, but why so important to observe in the infrared? Why we have spent so much money to develop a telescope that observes in the infrared? Well, there are several reasons. I will just mention a few. One of these is because with Webb, one of the goals of Webb is to see and characterize the atmospheres of exoplanets, so planets in other solar systems. And in the infrared is where we see the signatures of some of the most important molecules, such as water, methane, carbon dioxide, and so on. And I will not discuss exoplanets, but that is another area where Webb is is enabling a lot of progress. The other reason is that the interstellar medium in our galaxy, in any galaxy, contains a lot of small solid particles, which we call cosmic dust. And these solid particles, especially in regions where you have formation of stars, clouds of dense gas, there are so many that they essentially can absorb effectively the light in the visible, to the point that, as you see, we can hardly see any star in this dense cloud of where stars are forming. However, these dust grains becomes relatively transparent in the infrared, and we can, in the infrared, pierce through these clouds and see the formation of stars inside these clouds. So observing in the infrared allows us to probe the formation of stars in these dusty, dense clouds in our own galaxies, but also in other galaxies. The other reason is because we want, one of the main goals of Webb is to explore the formation of galaxies. We live in the local universe, so we see these splendid galaxies containing billions or even trillions of stars arranged in these grand design spiral patterns where stars are continuously forming with a bulge, a central bulge, which is a bit older. And one of the most important questions that astronomers are trying to answer is how these large galaxies were formed and how they acquired this morphology. And to answer these questions, we have to see how these galaxies were in the past. And for this, Webb is the perfect time machine. What you see here is a chart, an illustration of how we think the universe and how galaxies formed across the cosmic epochs. So after the Big Bang, there was a period which we call the Dark Ages, where essentially nothing was happening, only gravity was at work, and in the overdense regions, more and more matter, and particularly gas, was accreting. At some point in this region, the density was became so large that, and the pressure so large that the first stars could form. And that essentially was the first light in the universe. And subsequently, more and more stars formed, and these assembled in larger and larger galaxies, and eventually forming the galaxies that we see today. And Webb, as I mentioned, is the perfect machine to explore this cosmic evolution of stars and galaxies, because thanks to the large collecting area of its large mirror, can observe very distant galaxies. And observing very distant galaxies means observing back in time, because this is a consequence of the finite speed of light. And because observing galaxies very distant, it means that we don't observe those galaxies how they are now, but actually how they were when the light started traveling from those remote distances. And so the first stars and that formed in the universe were formed billions of years ago, and so the light that was emitted from them essentially started their journey billions of years ago, and so we are seeing them essentially how they were in the far past. Okay, and what does it has to do this with observing in the infrared? Well, the problem is that because of the expansion of the universe, as the light travels through the universe, its wavelength gets stretched, and stretching the wavelength means that the light becomes redder and going even into the infrared. And the farther the galaxies are, the more this stretching to the red and to the infrared becomes important. And essentially, if the most distant galaxies that we are observing with Webb, we can only see them in accessing indeed the near and mid-infrared, where they are essentially completely invisible in the visible wavelengths. And so that's why one additional reason why Webb was developed in such a way to be particularly sensitive at infrared wavelength. Now, before JWST, people, of course, had investigated how galaxies were evolving in the past, and with the instruments and the telescopes that we had at the time, the idea was that as we were observing galaxies back and back in the past, billions of years ago, their morphology was more and more clumping and irregular. So our understanding was that the early formation of galaxies was particularly chaotic, probably resulting from assembly of clumps of gas and stars, and that the formation of regular disks that we see in the local universe, such as the Milky Way, actually happened relatively late in the cosmic evolution of the universe. However, already with the first images from Webb, and this is one of those, it's the galaxies, the distant galaxies, actually appear to be quite different from what we had seen until that point, with many more structures that were resembling normal disks, and than we actually thought we knew before that. And just to give you an idea of the improvement in the capability of Webb in seeing these distant galaxies, this is an image obtained with a ground-based telescope of distant galaxies, and this is what James Webb has revealed in the same region. And you see these blobs that we essentially hardly distinguish from anything, just a clump of light. Turns out to be actually fairly regular disk galaxies. And of course, Webb also detects many more galaxies that were totally invisible from ground. And the comparison is also impressive with previous images from the Hubble Space Telescope. This is a galaxy far away that with Hubble looked like just an assembly of clumps, so very irregular galaxies. But when observed with the James Webb Telescope, actually turns out to be a relatively regular spiral, beautiful spiral galaxy. And this is a constant finding of Webb, of essentially many more distant spiral and disk-like galaxies than we were expecting. And this is a more quantitative illustration of this finding. In each of these panels, you see the statistics of the morphologies of galaxies that was found by the Hubble Space Telescope and later now with the James Webb, as a function of the look-back time. Essentially, this is what you see here is the age of the universe. So here we are is the current epoch, and this is essentially we are seeing is the look back time, how far back in the past we are seeing. Okay, and with the Hubble, you see that the main finding was that most galaxies were thought to be irregular and peculiar somehow, while only essentially there were essentially no regular disk galaxies with regular spiral patterns in the past. But with Webb, we are actually finding that the universe managed to form regular rotating spiral galaxies very early in the universe, and this was somehow expected by some theories and some models. This is a computer simulation of a box of the universe, showing that indeed, according to these models, the gas is funneled in streams towards the regions of high density of matters, and this gas start to settle in disks, and there, when the gas density becomes large enough, it starts to form stars, and these stars therefore forming a sort of disk-like pattern. However, it's still been surprising to find that these many disk-like and spiral galaxies, because we thought that this process could happen much later in the universe, and only for a small fraction of galaxies. While it seems that with Webb we are finding that actually a large fraction of galaxies evolve so quickly in this regular pattern. And so this is one of the findings that I will repeat on and on, that with Webb we are finding that everything in the early universe happened much faster and often more dramatically than we thought before Webb. This is a cartoon illustrating how we think, or we thought the universe was evolving. This was produced before the JWST, and so the Big Bang, then, as I mentioned, the Dark Ages, the formation of the first stars, and then slowly the formation of the assembly of galaxies. Now the overall picture qualitatively hasn't changed, but as I mentioned, we have realized that things happen faster in the early universe. In particular, now the most distant confirmed galaxies found by Webb is this little dot here, the red dot. Trust me, it's a galaxy, although it's barely resolved. And is found at an age when the universe was only 300 million years old. And the galaxy is found to have an age of about 70 million years. So must have formed when the universe was only about 200 million years. So this statement that the first stars formed about 400 million years ago actually has to be revised, and probably, as far as you can say, is probably the first galaxy and first stars started forming very much earlier, about 200 million years after the Big Bang. Now, I want to zoom a little bit on this galaxy. Neglect this is a foreground galaxy. So as you see, it's very red, as I mentioned, because it has been redshifted tremendously, because it's so early in the universe. And you can barely see that it actually has a structure, because it's really an embryo of a galaxy. And it's interesting to compare with the galaxy like the Milky Way. Okay, the Milky Way. So we are now the age of the universe now is about 13.7 billion years. The mass of the galaxy, of a galaxy similar to the Milky Way, is about 1 trillion times the mass of the Sun. And the size is about 100,000 light years. And this galaxy here that we have found, the most distant so far, called JWST, is actually only, has a mass of only 70 million times the mass of the Sun. and the size of just 150 light years. And this very likely is a progenitor of a galaxy like the Milky Way. So across the cosmic epochs, it will evolve into this. And you see, we'll have to grow a lot in size and in mass to become the Milky Way. But the embryo is there. It's quite impressive how the journey of these galaxies through the cosmic epochs. With Webb, of course, we are tracing this evolution. And for instance, a student here in Cambridge, I don't know if it is Norwegian, William Becker, found this other galaxy a bit later on. Now we are at an age of the universe of 700 million years. And you see that the galaxy is already a little bit bigger, but more interestingly, it already has some structure. It has a central older core, and you start to see something around it, which is actually the first version of a young disk, and possibly a clump, which is probably another small galaxy that is merging with it. And this is a more quantitative description. This is the radial profile of the light that's showing the core and how the stance of the core and the disk. But essentially, this is already a galaxy like the Milky Way in miniature. It already has its small version of the core of the galaxy, the old bulge, and the disk is simply much smaller than the galaxy, but it has already its component. And this is also fascinating because it means that, again, the universe managed to make this small version of this galaxy, like the Milky Way, already in place so early in the universe. We were not really expecting this. I must say that most of the interesting results from Webb, I may be a bit biased in this, actually are coming from some of the instruments which are providing a spectrum, the spectrum of the galaxies. For those who are not familiar with the spectrum of the light or anything, is essentially the decomposition of the light in its color, essentially the rainbow of the light, okay? And Webb is extremely powerful in this. It has an excellent set of instruments which can provide different kinds of spectra. And actually, the most used is an instrument that actually uses a simple prism, that's simple, of course optimized for the infrared, but a prism like this one. And most of the observing time, in contrast with the Hubble, which had some spectroscopic capabilities, but not very much used, most of the time, observing time with Webb is actually used to take spectra of exoplanets, galaxies, and distant galaxies. And we learn a lot from the spectra, or the rainbow of galaxies and stars, because from the rainbow or spectra of stars, we can learn, for instance, their temperature, which is connected with their age. But if you have a gas, so for instance, the glass in a light bulb, the spectrum has specific peak of specific colors that are associated with transitions of the atoms that are contained in the gas of the bulb. And the same applies for galaxies. Galaxies have plenty of gas, which is excited in different ways. And from the colors that we get from the spectrum, we get important information about the properties of the galaxy, and particularly about their chemical composition. And for us astronomers, indeed, one of the most mind-blowing revelations from the very first data from Webb, which were released in June 2022, were these spectra like this. This is the spectrum of a galaxy observed more than 13 billion years ago, so back in the past. And it was really fantastic for us and also puzzling from some aspects. Because you see that there are all of these signatures of hydrogen, and that's not surprising because the hydrogen is the most common chemical element produced by the Big Bang. And then the second most abundant is helium. But apart from hydrogen and helium, and some traces of lithium, all the other elements have been produced later on by the nucleosynthesis in stars. So finding the so strong features associated with oxygen and neon was actually quite surprising for us. Just to clarify where these elements come from, as I mentioned, Big Bang only produced helium and hydrogen and traces of lithium. Then all the other elements comes from the formation of stars. Stars form as a consequence of the gravitational collapse of gas clouds. And some stars form very big and very massive. And when they explode as supernovae, they produce various chemical elements such as oxygen, magnesium, and so on. Smaller stars end their lives by ejecting their outer layers and inject into the interstellar medium elements such as carbon and nitrogen. And then all of these elements are then recycled in the gas clouds to form the next generation of stars. So the more time passes, the more the stars and the interstellar medium gets enriched with chemical elements. And this happens in the star-forming regions of our galaxy, within galaxies, and also across the universe. So as I mentioned, after Big Bang, only helium, hydrogen, and lithium were produced. And from these, the gravitational collapse of the gas clouds containing only these pristine elements formed the first generation of stars, which we call population 3. And I will come back to this. These exploded as supernovae and enriched with more heavy chemical elements. And these were then used by the next for the formation of the next generation of stars later on. And if you consider the composition of the elements, the origin of the elements in the solar systems, and even in our own bodies, only less than 10% of the chemical elements in our bodies are actually coming from the Big Bang. The vast majority come from chemical elements which have been produced by stars of different masses. And different stars with different lifetimes produce different kind of elements. And if you take a simple case of a cloud of gas which collapses and forms different kind of stars, these, as they die, they inject, they produce chemical elements and inject them into the interstellar medium. And this is the kind of evolution of enrichment that you obtain from this star formation. The oxygen typically forms very quickly because it's produced by very massive stars which are short-lived, and then carbon, nitrogen, and then iron. Now, this is a very simplified case. In real galaxies, the process is much more takes much longer. Is much more slow because you have subsequent generation of stars which keep enriching the interstellar medium, and at the same time you keep having inflow of pristine gas from the intergalactic medium which dilute the chemical enrichment. So it's a more complex process. So if you go back to this illustration, while you form stars across the cosmic epochs, you produce more, you convert gas into stellar mass, and at the same time you enrich the interstellar medium and the stars with more and more chemical elements. And that's what we are trying to trace back with Webb. And I will try to illustrate you what we are finding with Webb. Don't get scared. This is a bit busy plot, sorry, but I'll drive to it. So it's a very important result from Webb. So what you see here is the abundance of oxygen relative to hydrogen. So the more you go up, the more you have oxygen, okay? The more has been the chemical enrichment. And as a function of the mass of the galaxies, the stellar mass of galaxies. And of course, the more massive a galaxies, the more you have oxygen because you have produced more stars which have released oxygen and other elements in the interstellar medium. However, the main point is that here are all new measurements by James Webb, and the most distant of these chemical measurements is around when the for galaxies which are when the universe was about only 400 million years after the Big Bang. And the chemical enrichment of oxygen was already at that time about 10% of their final amount of chemical enrichment, which is remarkable because for 100 million years, it's quite early in the life of the universe. It's about 3% of the whole life of the universe. So in the first 3% of the lifetime of the universe, somehow the formation of stars have already enriched quite a lot the stars and the interstellar medium. So again, we see from Webb that the universe has evolved very quickly. Everything has happened much more fast than what we thought. Okay, everything has been more dynamic and more exciting in the early universe. This is the most distant detection of a chemical element heavier than helium, actually heavier than hydrogen, I would say, detected so far with Webb. And this was obtained by, has been obtained recently by a postdoc, Francesco Eugenio, here in Cambridge, and is this detection of carbon and some traces of oxygen when in this galaxy, which is nearly the most distant galaxy, again, is a tiny blob. And we are now at about 350 million years after Big Bang, so really shortly after Big Bang. And this is exciting. We see a lot of carbon in this galaxy, more than oxygen. And, but there is something wrong here, terribly wrong. What is wrong? Anyone can spot it? Okay, the problem, if we go back to this plot here, you remember that the first element that should appear in galaxies should be oxygen, while carbon lags behind. Instead, this is the first galaxy in which we see chemical enrichment, and the carbon is much more abundant than the oxygen. So what's going on is potentially very puzzling. Well, a possibility is that actually we are seeing the fingerprint, of the chemical fingerprint of the first generation of stars. Indeed, there are some models according to which the enrichment of the first of the supernova explosions associated with the first generation of stars, the population 3 stars, actually produced much more carbon than oxygen. And so in this case, we can indeed explain this in terms of, can explain the abundances of carbon and oxygen that we see in this early object. Now, this is an indirect indication of the products of the first generation of stars, but can we actually see directly the first generation of stars, this population tree that formed in the early universe? Well, it's very challenging. So what do we expect to see? Well, the first a generation of stars should have no chemical elements heavier than helium. As we said, they were born from pristine gas formed by the Big Bang, so only helium and hydrogen. They, according to theory, they should be, because of this low level of chemical elements, they should be very massive, very hot, extremely hot, and their radiation, their light, should be so energetic that it should be capable of ionizing helium twice in their surroundings. Okay, so we have been looking for this, and we have obtained this initial tentative result, which will, by the way, you will see this in a press release by NASA next week. Sorry, and so what you see here is a galaxy that was already known at far away. Again, we are about 440 million years after the Big Bang, which is this one. And in the halo of this galaxy, we found this signature of doubly ionized helium and no evidence for any other metal lines. So this could be indeed a signature of for the formation of the first generation of stars, population 3, in the halo of this galaxy. The problem here is that this cluster, or putative cluster of population 3 stars, is quite massive, so we are trying to understand, while we were expecting to be less massive, so we are trying to understand why is that, and there are various possibilities that, if you want, we can discuss later on. Note that this other galaxy also has helium-2 emission, so doubly ionized helium, but this is not because it's hosting population 3 stars, sorry, but it's because it's hosting an accreting supermassive black hole. And this allows me to link to the final bit of this lecture, which is about the supermassive black holes. We know that essentially in the center of most galaxies, there are black holes which have masses between millions to billions times the mass of the sun. And we identified them. We can't see, of course, the black holes, but what we see is the gas swirling around the black holes, which is accreting onto it and becomes very hot, and this forest starts to become very bright, and its glow often is so strong, so bright, that it outshines the galaxy in which they live. And also often we see the evidence of the gas surrounding the black hole, which is very dense, moving very fast, and highly ionized. And we know, for instance, that there is a black hole in the center of our own galaxy. This is a zoom of the central cluster in our galaxy, and the motions of the stars around in the galactic center have been the first clear evidence for the presence of a huge mass, invisible mass, identified as a black hole with about 4 million times the mass of the sun in the galactic center, which gave the Nobel Prize to the discoverer a few years ago. And more recently, this has been, the shade of this black hole has been imaged by the Event Horizon telescope. Now, and as I mentioned, our galaxy is not peculiar. We think that most galaxies have this kind of supermassive black holes at their centers. Now, how did these very supermassive black holes grow so large? This is the standard scenario, that you have a massive star, which masses between about a few tens or even hundreds times the mass of the sun. They live very, very short, and when they die in supernova, they may leave behind a black hole with a mass of tens or something, possibly 100 solar masses. Then this black hole accrete matter gas from the surrounding, from its host galaxy, and grow until potentially can reach these masses of millions or billions times the mass of the sun. What is the problem? The problem is this step here. The black hole cannot be too greedy. According to theory, there is a limit at which the black hole can accrete. The problem is that as more gas swirls around the black hole, it becomes more and more hot and radiates more and more energy, and the light emitted by this so-called accretion disk start to put pressure on the matter around the black hole. At some point, if it accretes too voraciously, the radiation of the radiation pressure on the atoms is stronger than the gravitational pull. At that point, the black hole sort of suicides because essentially expels the matter out of which it's feeding, and therefore the accretion slows down. So this is a sort of self-regulating mechanism in principle of black holes. Okay. And now, what is the problem? Already a few years ago, astronomers had discovered black holes in the early universe. We are talking now about ages of close to 1 billion years after Big Bang. And the problem was that these black holes are fairly massive. Well, actually, I would say hypermassive, with masses of billions times the mass of the sun. And the problem is that if you try to see if you try to explain their masses by accretion on stellar remnants with this Eddington-limited mode, you struggle to explain them because the seeds should have formed essentially soon after Big Bang, which is very difficult to envisage. The way to understand this is to explore this pattern of accretion and evolution by searching for smaller black holes and at earlier epochs. And Webb has been fantastic for this. And this is, there's been a lot of works by international teams, and here in Cambridge we are extremely active. I would say we are one of the leading institutes in this area. And with Webb we have identified dozens now of these intermediate mass black holes in the early universe. And they are, in the imaging, in terms of images, they appear like simply point source, but their spectra show evidence of very dense gas moving very quickly, and very highly ionized atoms, which are all typical of gas in the vicinity of a supermassive black hole. And we are finding dozens of them. And this is the most distant of them all, discovered again here in Cambridge, which you may have seen some was on the newspaper in December and then also in January and so on. And it has a mass of about 2 million solar masses, and discovered when at an age when the universe was about 440 million years after the Big Bang. You can see that this black hole probably can be the progenitor of those more hypermassive black holes that are found at later epochs. And you see that we have pushed back in time the problem of how these black holes are formed. In particular, if you assume that this black hole has accreted at this Eddington limit, you can hardly explain it with simple stellar remnants. You would have formed again probably immediately after Big Bang. So astronomers have come up with alternative theories to explain these early black holes. One possibility is that the seeds were indeed formed by the collapse of the first generation of stars, the so-called population tree stars, which formed the initial seeds with 10, 100 times the mass of the sun. But then they were extremely greedy. They globed matter at a rate much higher than the so-called Eddington limit, so exceeding this limit. And according to some theory, it's possible to have this super-red internal accretion. And actually, this black hole that we have found, is the most distant black holes, is indeed found to eat gobble matter at a rate which is 5 times higher than this Eddington limit. The other possibility is that the stars form in very compact nuclear clusters at the center of galaxies, and they merge very quickly to form more massive seeds. And another possibility is that black holes simply were born big. And this is a scenario, the so-called direct collapse black holes, according to which the pristine massive clouds of gas in certain conditions could collapse to form a massive protostars, which would then collapse to form black holes directly, which are already very massive, about 100,000 times the mass of the sun. And when you are already so massive, it's then very easy to form this kind of million times black hole masses. So in either way, these black holes in the early universe have formed very, very, very quickly, even more quickly than galaxies. So I already said that galaxies, Webb has revealed that everything happened faster in the universe. Galaxies formed very quickly. Actually, black holes formed even faster than galaxies. And to illustrate this, let me show this diagram, which is a well-known relation in the local universe, which is the relation between the mass of the black holes and the mass of their host galaxies. And so in the local universe, we know that black holes have a mass which is about 1,000 times smaller than their host galaxy, so are relatively small. However, what we are finding with Webb is that as you go to look at these black holes in the early universe, they are far more massive relative to the host galaxy. So this is the same local relation that I showed you. And these black holes that we are finding in the first billion years of life of the universe are actually much more massive than what is expected by the local relation. Some of them are nearly as massive as their host galaxies. This is a work of a student here in Cambridge again, that is here in the audience. And this is quite impressive. So actually, this means that black hole formed very quickly and the galaxy lagged behind, and only later on, throughout the cosmic epochs, the galaxies managed to grow in stellar mass. And again, these can be explained either these black holes born big, or actually that they were very greedy, very voracious, and gobbled a lot of matter very quickly in the conditions that of the early universe. I'll finish by mentioning one thing that I haven't discussed so far, that is galaxies also merge between them. In the local universe, this is a relatively rare phenomenon, but in the early universe was much more common. And when they merge, the black hole at their centers can also merge. And this can be a potential additional mechanism for growing black holes. And Webb is also revealing that this is indeed the case in the early universe. This is a recent result by a postdoc here, a fellow, Kavli fellow, Hannah Hubler in Cambridge, finding that in the discovery of black holes which are offset from the center of the galaxy, so are in the process of merging. And the finding is that there are quite a few of them, and so this indeed can be an additional mechanism through which black holes can grow very, very quickly in the early universe. And when they merge, they will produce gravitational waves, and that will be detectable with future space missions that are being developed by the European Space Agency, such as LISA, which has just been approved. So I will conclude by saying that James Webb has revealed that everything is happening faster in the early universe, everything more dynamic, probably even for us more exciting. But just warning that this is just the beginning. This is just the first year and a half of results. And the bulk of the results will come in the coming years. So thank you.